Hello, welcome to this lecture series on electronic properties of materials. This is lecture number 13. In the last lecture, I just started the Sommerfeld theory of free electrons in metals, or also called as quantum free electron theory of metals. Okay, and I told you that the approach of Sommerfeld is that the free electrons are treated as quantum particle instead of classical particles. Okay, very specifically they are fermions because they have half integer spin. Okay, then based on that we constructed the Schrodinger equation for the free electron, and we solved the Schrodinger equation. Right, after solving the Schrodinger equation, we get the wave function psi k of r in third dimension as 1 by square root of v into e power iota kx into x plus ky into y plus kz into z. Then the energy for for the particle, the energies of the electron are quantized. Okay, electrons, the free electron can take only quantized energy values, and the energy values are obtained by using the equation Ek equal to h bar square by 2m into kx square plus ky square plus kz square. Okay, this is the expression for energy, and this is the expression for the wave function. So the wave function and the energy depends on the value of kx, ky and kz. Remember, kx, ky, kz takes only certain quantized values, right? What are the quantized values? You know very well, kx equal to nx 2 pi by L. Okay, nx 2 pi by L. Since nx can take only certain allowed value 0, plus or minus 1, plus or minus 2, etc. Therefore, kx also takes only certain allowed values. Clear? It cannot take just like that any value. It takes only certain allowed values. Therefore, energy is also quantized. Okay, energy cannot be continuous. Energy is also quantized. Right? Now, for a particular value of energy Ek, suppose let us assume that energy is Ek. Bring this 2m h bar square to the left hand side. You can write kx square plus ky square plus kz square as 2m Ek by h bar square. For a given value of energy, suppose the free electron, suppose you take some free electron, let us fix the energy as Ek. If energy is fixed, then this right hand side become a constant. If the right hand side quantity is a constant, you can call this equation as equation of a sphere in k space. Clear? So if this become a constant, this equation behave like an equation of a sphere. Clear? Now listen, this kx square plus ky square plus kz square is shortly represented as k square. So k square equal to this. K square equal to 2m Ek by h bar square. Right? If this is a constant, then k is nothing but radius of that sphere. Radius of the sphere. Suppose if I take, say if this is k square, then this should also be k square. If this is k square, then as per equation of sphere, if this is a constant, then that k square is a constant. Therefore, the corresponding k is nothing but the radius of the sphere. Clear? Now, if I draw using kx, ky, kz axis, if I draw a sphere, okay, that sphere is what we call as that is a sphere for the for a particular value of energy Ek. Okay, let me show that in the next page. Yeah. So now I'm going to focus on k space and k states. What is k space? So if I plot this kx value, ky value and kz value, okay, I'll took, see here I took three perpendicular axes. So this is kx axis, this is ky and this is kz. Okay, for a particular value of energy, then the right hand side quantity become a constant, you will get a sphere. Okay, this is the sphere for a particular value of energy Ek. So here at the surface the energy is Ek. Okay, now what we are going to do is a set of kx value, ky value, kz value will give you a state. I repeat, one particular value of kx, one particular value of ky, one particular value of kz will give you a state. Right. So within this ek, or within this sphere, there are many possible values of kx, ky, kz. Right. So there are many states available inside this sphere. Okay. So now what I'm going to do, listen. Suppose, see, what are the possible value of kx? You know, kx equal to nx into 2 pi by L. Right. If I put nx equal to 0, right, then kx becomes 0. Similarly, ky equal to ny into 2 pi by L. Similarly, kz equal to nz into 2 pi by L. Clear? If I put nx 0, ny 0, nz 0, then kx, ky, kz all become 0. Therefore, that becomes the origin of, that represent a state, and that is nothing but the origin. Clear? Then if I put nx equal to plus 1, okay, ny, n is as 0, then I'll get a state here, and the length of this point from the origin is nothing but 2 pi by L. If I put nx equal to 1, then this length is nothing but 2 pi by L. Okay, so this point represent kx value 2 pi by L. Okay, if I put nx equal to 1 and ny 0, n is at 0, therefore ky, kz also 0. So this point represent 2 pi by L 0, 0, 0. What about this point? This point represent here nx is 0. Okay, so kx is 0. Put ny as plus 1. If I put ny as plus 1, I'll get 2 pi by L here. Then nz as 0. So this is a second point. Okay, it represents the point along ky axis, first point along ky axis, and again this length is also 2 pi by L. Similarly, the first point along kz axis in the positive direction, this length is also 2 pi by L. Clear? So each point in this, listen here, I put points along the axis only, but don't think that we have states only along the axis. It is also present, okay, in space, in 3D space. Okay, now what I'm going to do, let me choose a point here. Listen, suppose I'll take this as kx axis, this as ky axis, and this as kz axis, right? And this is the origin. Origin represent a point that is 0, 0, 0. Okay, then I'll take a point. Say for example, I'll take a point 2 pi by L along x-axis, kx axis, 2 pi by L along ky, and 2 pi by L along kz. So kx, ky, kz all are taking value 2 pi by L. Where is that point? See, suppose this is the length 2 pi by L along kx axis, this is 2 pi by L length along ky axis, and this is 2 pi by L length along kz axis. Then that point should be in 3D space. Okay, let me represent that point with this by drawing a cube. Let me show that here so that you can easily understand. Let me draw a cube. Then this point, see this corner point. Okay, origin is this 0, 0, 0 represent this point. I am talking about this corner point. This corner point is nothing but 2 pi by L, 2 pi by L, 2 pi by L. Okay, now listen, from this point, and you see the points along the axis. Okay, in between there are no other points available. Each point represent a state. Now what I'm going to do, what is the volume of this point, right, from the origin, or what is the smallest volume that is possible for a particular state in k space. Okay, see the space which is present by keeping the axis ky, kz, ky, kx, ky, and kz. If you plot anything in this graph or in this three-dimensional space, we call that space as k space. Okay, in k space each point represent a k state. Okay, now listen. So a set of kx, ky, kz. Right? If kx 0, ky 0, kz 0, that set represent one state, one k state. If kx is 2 pi by L, ky 0, kz 0, that represent another k state. If this is 2 pi by L, this is 2 pi by L, this is also 2 pi by L, that represent another k state. So in k space we can actually create, or we can actually have many states. Okay, many allowed states are there. And we also know that electrons are fermions. Okay, so they have clockwise spin and anti-clockwise spin, right? So each k state can occupy or can take only 2 electrons. So in each of this point, I repeat again, each point in this space represent k state. Each state can accommodate maximum of 2 electrons. Okay, then along the axis, the space between any 2 neighboring k states, you take any 2 neighboring k state, right, along the axis, the length is 2 pi by L. Clear? Then now let me move on to the next one. Now, what is the volume of k space per k state? Or we can say that the smallest volume occupied by a state. What is the smallest volume occupied by a state? For that you take a point. Say I'll take a point in k space, in 3D space, not along the axis. I am taking some point in the space. Now what is the volume occupied by this point? Okay, so see, here we have a state, here we have a state, here we have a state, correct, but in between there are no other states. So this volume, the volume of this cube, is nothing but the volume occupied by this k state. Okay, now so what is the smallest volume? The smallest volume occupied by, that's what given here, smallest volume occupied by a state is nothing but 2 pi by L along a kx axis into 2 pi by L along ky and 2 pi by L along kz. That gives you, okay, this is length along kx axis, length along ky, length along kz. If I multiply all the 3 length, I will get the volume of that small cube. Volume of that small cube is nothing but smallest volume occupied by a state. Okay, so if I multiply, I will get 8 pi cube by V. L into L into L is L cube. L cube is nothing but volume of the cube. Clear? So I'll get 8 pi cube by V. This is the volume occupied by one state, okay, in k space, or the smallest volume occupied by a state, right, in k space. Clear? Now the question is number of k states per unit volume. See, this is states, okay, volume occupied by one state. Volume occupied by one state is this much volume. If one state occupies this much volume, what is the volume or how many states are there per unit volume? What you have to do? Listen, one state, for one state the volume occupied is 8 pi cube by V. So now what is the number of states occupied by one unit volume? For that you have to divide 1 by this, correct? So number of k states per unit volume, if you want, number of states per unit volume is also called as density of k states. Okay, so if you want this quantity, what you have to do? Divide this 1 by 8 pi cube by V. So this V will go to the numerator. So V by 8 pi cube is the number of k states which are possible, right, in one unit volume. Right, number of k states per unit volume is nothing but equal to V by 8 pi cube. Clear? Yeah. Now I'll bring one more concept here. Okay, we will discuss about this concept. Then I will incorporate, okay, this information in this concept. Okay, you know very well electrons are fermions because they have spin value half, spin quantum number value is half. So electrons are fermions. They obey Fermi-Dirac statistics. Clear? Electrons are fermions. Fermions obey Fermi-Dirac statistics or Fermi-Dirac distribution. Right? According to Fermi-Dirac distribution, the probability of occupancy of a state Ek, right, state having energy Ek. What is F? F is nothing but probability of occupying, okay, a state having energy Ek is equal to 1 by e to the power Ek minus Ef by kBt. This is Ef. Ek minus Ef by kBt plus 1. Okay, what is Ef? Ef is nothing but Fermi energy. Fermi, E is nothing but Fermi energy. Now, so Ef is Fermi energy. Now observe carefully. If I plot F of Ek, that is probability of occupying a state having energy Ek versus energy Ek. Okay, so for different value of energy, what is the probability of occupying a state? If a state is fully occupied, probability is 1. Clear? You know very well, as we move, suppose I'll take one dimension. In one dimension, listen, assume that these are all energy values. These are all possible energy values. Right? We have many states like this, and each state is occupied by two electrons actually. So 2 electron, 2 electron, 2 electron, right? It goes like that. Now see, the ground state is fully occupied. Therefore, probability of occupancy of this state is 1. Next level is also fully occupied. Next state also fully occupied. Next state also fully occupied. Like that it goes. If the state is fully occupied, probability is 1. Clear? Now, so this is Ek equal to, say, this is the ground state. Say Ek equal to 1, Ek equal to 2, like that. Okay. Now, see, at 0 Kelvin, students observe carefully. At 0 Kelvin, see, many levels are occupied. Then all these levels are occupied. Just imagine like that. Okay, we have a level, top level, which is also occupied. Above this level, all other levels are empty. Just imagine like this. Okay, we have a system where the free electrons occupy the available states. At 0 Kelvin, okay, all the lower states are occupied. Okay, up to a certain state it is fully occupied, right? And we have a state here. Let me put this state here. The highest occupied state, listen carefully, the highest occupied state at 0 Kelvin, energy of this state is what we call as Fermi energy. I repeat, at 0 Kelvin, okay, lower levels are fully occupied. Okay, if you go above and above and above in the increasing order of energy, right, we get an upper state which is fully occupied. Above that state, all other states are fully empty. Okay, the state which is fully occupied, the top state, okay, the highest energy state, right, which is fully occupied, the energy of that state is nothing but Fermi energy. Okay, so there exists a Fermi energy EF, right, at 0 Kelvin. At 0 Kelvin up to Fermi energy, all the states are fully occupied, so probability is 1, 1, 1, 1, 1. Goes like this. After Fermi energy, all the levels are fully empty, therefore probability is 0, 0, 0. So below EF, all the levels are fully occupied, so probability is 1. Above EF, all the levels are fully empty. Okay, so this energy is what we call as Fermi energy. What is Fermi energy? I repeat, at 0 Kelvin, the highest occupied level, the energy of the highest occupied state, okay, is nothing but Fermi energy of that state. Is the Fermi energy, I'm sorry, Fermi energy of that system. I repeat, at 0 Kelvin, the highest occupied state, okay, energy of that state is nothing but Fermi energy. Right? At 0 Kelvin, the states below Fermi energy are fully occupied, so probability is 1. States above Fermi energy are fully empty, therefore the probability is 0. So this is at 0 Kelvin. This graph represents at 0 Kelvin. Clear? Now what I'm going to do, first we'll do the calculation at 0 Kelvin. Then we'll see what happen if I supply heat to the system. If I increase the energy of the system, what will happen? That we'll discuss as we go along. Okay, yeah. So let me start with the calculation of number of free electrons and other things at 0 Kelvin first. Okay, yeah. Now listen carefully. Let us consider there are n free electrons available in volume V. Okay, V is the volume of the metallic piece. I told in the last lecture we took a cubical piece of metal and volume of that metal is V. Let us assume that metal piece contains n number of free electrons. So n is the total number of free electrons available in the metal of volume V. Now first we start our calculation at 0 Kelvin. At 0 Kelvin, okay, n electrons are n electrons occupies, okay, we have n electrons, the n electrons occupies up to the level EF, correct? At 0 Kelvin, right, all the levels up to EF are fully occupied. Okay, so all the n electrons occupying from the ground state onwards, it occupies all the states up to the Fermi level, right? Now therefore the equation of sphere, so now the highest energy is EF. EF is a fixed value for a given metal, right? So if I put E in the place of EK, if I put EF, okay, EF is a constant quantity, so this become a constant now. Okay, this become a constant, and this is equal to KF square. It's a constant. Let me take that constant as KF square. So KF square equal to 2m EF by h bar square, and where KF is nothing but radius of that sphere. When I put EK as EF, when I put EK value as EF, you will get some constant value here. If this is a constant, then this equation becomes a sphere. Okay, the radius of that sphere is nothing but KF. Okay, and listen, we get a sphere. That sphere is called Fermi sphere. Fermi sphere. Okay, so what is Fermi sphere in K space? Let me just draw and show you. In K space, so this is Kx axis, this is Ky axis, and this is Kz axis. In K space, I'll draw a sphere with a radius. Let us assume that this is a sphere of okay, we have a sphere here. Let us assume that this sphere has some radius, let it be Kf. Okay, listen, at 0 Kelvin we have many states inside this sphere. All the states are fully occupied, okay, in three-dimensional space, right? At 0 Kelvin all the states inside the sphere are fully occupied. On the surface also fully occupied. Okay, above the surface we have many states which are all empty. Clear? And this sphere is what we call as Fermi sphere, right? And radius of the Fermi sphere is represented by the symbol Kf. Okay, Kf is the radius of the Fermi sphere here. Now what is the volume of the Fermi sphere? You know very well, the volume of the sphere formula is 4 by 3 pi r cube. So 4 by 3 pi, and the radius is Kf here, so Kf cube. This is the volume of the Fermi sphere. Clear? Now so number of K states in Fermi sphere is, okay, within the Fermi sphere, how many K states are there? Listen, you know very well, number of states per unit volume is V by 8 pi cube, which we have already discussed. Correct? In 1 unit volume, how many states are there? V by 8 pi cube states are there in 1 unit volume. Then how many states are there, right, in this volume? This is the volume of the sphere, also called Fermi sphere. So in Fermi sphere, how many states are there? If this is the number of states per unit volume, if I multiply this with the volume of the sphere, I will get total number of states available in Fermi sphere. So number of K states in Fermi sphere is equal to 4 by 3 pi Kf cube into volume of into number of states per unit volume. If you multiply these two, and we know very well each k state can take 2 electron. Therefore, remember, at 0 Kelvin all the states inside the sphere on the sphere are occupied. Above the sphere all the states are empty. Clear? Therefore, the entire n electrons of the metal are present, right, only within the Fermi sphere, right? Therefore number of electrons, total number of free electrons is equal to, right, so this quantity is nothing but number of states available in Fermi sphere. Each state can accommodate 2 electron. Therefore, if you multiply this value by 2, I will get total number of electrons. Okay. Now, how to calculate number of free electron per unit volume? This is total number of electron and volume of the metal is V. So if I divide N by V, I will get number of free electron per unit volume. So here, what is NF? NF is number of free electrons per unit volume, which is nothing but NF. NF is equal to capital N by V. So what I'm doing here, bring this V is in the numerator, bring the V to the left hand side, you will get N by V, and N by V is nothing but NF. So NF is equal to, see here, 4 into 2, 8, and here also we have 8 cancel. We have 1 pi in the numerator and pi cube in the denominator. If I cancel these two, I'll get pi square in the denominator. So what we get is 1 by 3 pi square into kf cube. What is this? This is nothing but number of free electrons per unit volume, which is given as 1 by 3 pi square into kf cube. Clear? Now, what is the radius of the Fermi sphere? If you want, bring this 3 pi square this side and take the cube root. So kf is equal to 3 pi square nf whole power 1 by 3. This is the radius of the Fermi sphere. So if you want to calculate radius of the Fermi sphere, listen, you just calculate number of free electron per unit volume. For a given metal, you calculate number of free electron per unit volume, substitute this value here and calculate this quantity. That quantity is nothing but radius of the Fermi sphere. Clear? Now, what is the Fermi energy? You know very well, the general formula for energy is Ek equal to h bar square by 2m, okay, into kx square plus ky square plus kz square, right? Now that sum is equal to kf square, correct? That sum is nothing but kf square if the level is Fermi level. If the level is Fermi level, then if the sphere is a Fermi sphere, then the sum kx square plus ky square plus kz square equal to kf square. Okay, right? If I take Fermi sphere, then the energy becomes Fermi energy, right? Fermi energy. So Fermi energy EF is given as h bar square by 2m into kf square. Okay, then EF is equal to h bar square by 2m. You know the value of kf equal to this, and you take the square of this. Okay, take the square of this, you'll get whole power 2 by 3 here, right? So h bar square by 2m into 3 pi square nf whole power 2 by 3. What is this? This is the Fermi energy of the given metal. So if you want to calculate Fermi energy of a given metal, alright, you know the value of h bar square. 2 m is mass of free electron, 9.1 into 10 power minus 31 kg. You know that value. 3 pi square. If you calculate NF, what is NF? Number of free electron per unit volume. If you know the value of NF, you can calculate the Fermi energy of the metal. Okay, so you can calculate Fermi energy of the metal by knowing the value of NF, right? Then see, I'm discussing all these quantities at 0 Kelvin. Keep this in mind, because at 0 Kelvin, right, all the states inside the Fermi sphere or on the Fermi sphere are fully occupied, right? Above the Fermi sphere, all other states are completely empty. Clear? Now let me define another term called Fermi momentum, right? Fermi momentum means the electron present on the surface, right? What's the momentum of those electrons? In general, what is the Fermi momentum? Fermi momentum is, real momentum is nothing but, see, we have a formula here. Listen, de Broglie equation, lambda is equal to h by p, or p is equal to h by lambda. Clear? If I rearrange, I'll get this. Now what I'm going to do, listen, I'm going to divide this h by 2 pi. I'll divide this h by 2 pi, and I'll multiply this 1 by lambda by 2 pi. So what I did, I just multiplied the numerator and denominator by 2 pi. Okay, and I wrote the equation like this: 2 pi by lambda into h by 2 pi. What is h by 2 pi? H by 2 pi is nothing but h bar or h cross. 2 pi by lambda is called the wave vector, which is represented as k. This 2 pi by lambda is actually represented as k. So momentum, right, can be related with the k as p is equal to h bar into k. This is well known, right? So Fermi momentum is equal to h bar into Fermi k value, okay, kf, right? So Fermi momentum equal to h bar into, the value of kf. Kf is equal to 3 pi square nf whole power 1 by 3. We had discussed in the previous page, right? And we also know that, so this is the formula for Fermi momentum. If you know number of free electron per unit volume in a given metal, you can calculate the Fermi momentum of the metal. Clear? Fermi momentum at a given temperature, right? Listen, very well, momentum is nothing but mass into velocity, right? So that Fermi momentum can be written as mass into Fermi velocity equal to this. Bring this m to the right hand side, and this is nothing but Fermi velocity of the given metal. Fermi velocity. Fermi velocity is a constant. Okay, that is the velocity with which the electron present on the surface can move, right, at the 0 Kelvin. Okay, so this is called Fermi velocity. Now, the expression for Fermi energy. Fermi energy equal to h bar square by 2m into 3 pi square nf into 2 by 3. If I rearrange this, I can write number of free electron per unit volume equal to 1 by 3 pi square. Very simple. You just bring 2m to the left hand side, h bar square to the left hand side. You'll get 2m by h bar square whole power 3 by 2. Then because I am taking here we have 2 by 3, we need to find out nf. Therefore you should make 3 by 2 square root, right? Okay, so first bring this 2 by m h bar square by 2m to the left hand side. You'll get 2m by h bar square whole power 3 by 2. Then ef whole power 3 by 2. Then bring this quantity 1 by 3 pi square. Okay, so very simple mathematics, you can easily rearrange. Okay, yeah, so this is the equation by which we can calculate number of free electron per unit volume. To calculate number of free electron per unit volume, you require Fermi energy. If you know Fermi energy, you can calculate this. And this is a very, very important expression, right? What I'm going to do in the next class is that using this expression, how to find the density of states. Okay, we have a standard expression for density of states. Okay, we are moving towards that. Once you know the expression for density of state, right, then we can calculate what happens when we supply some amount of heat to the metallic solid. See, we are at the temperature of 0 Kelvin. If we supply heat, temperature will rise up. If temperature rises up, okay, what happens if temperature rises up, the electron starts to move above Fermi level. If electron starts to move above Fermi level, okay, what happens to the electronic contribution to heat capacity, right? And we are going to calculate the other quantities based on this. Okay, yeah, I stop here. Thank you for listening.